Hello, this is the online lecture for General Physics 2 dealing with electric fields and field lines. Electric fields are admittedly an abstract idea. In some sense you could argue that they're something that physicists have made up in order to help them think about the way the world works, and in some sense that's true. They can be difficult to visualize, they can be abstract to think about, but they are something that was created to make thinking about certain situations easier. If we put in context what we've done so far, we've shown that things that have electrical charges are attracted to or repelled from one another, and we've put together a law called Coulomb's law that can describe how large the force is between those interacting charges. If we just left it at that, in many situations where we want to figure out what the force is on a certain object due to the electrical interactions that it's undergoing, if you have a situation where it's more than a handful of point charges, only having the idea of electric force would make a problem like that incredibly difficult, and hence we introduced this construct of an electric field, because the electric field ultimately lets us ignore one of the two things in an interaction, and if we know something about the electric field, we can ascertain what the force is on another object due to that field. And that probably doesn't make a ton of sense. Hopefully it will make a little more sense after we go through this discussion. Some of you may have talked about gravitational field in your Physics 1 class, and if so, that will be useful to you because there are many parallels between gravitational fields and electric fields. If you've not been introduced to gravitational fields, don't worry too much about it. I'm going to talk briefly about them here and then use that as a parallel to talking about electrical fields. So imagine on the left here is a mass. Well, that mass only experiences a gravitational force on it if it is near another object that has mass, and the one we're most familiar with is talking about it being near the Earth. So when there is an object that has mass and it is near the Earth, we say that this object experiences a gravitational force due to the Earth. The Earth, in turn, by the way, experiences a gravitational force due to this mass. Newton's third law states that. So we have ways of constructing calculating rather how large the force is on this mass. Well, if we took the mass away, we no longer can talk about forces because we no longer have two objects that are interacting. We could, however, talk about the area around the Earth and imagine that the area around the Earth is an area that contains something we call a gravitational field. And all that means is it's a way of that I'm describing the area around the Earth. And in fact, when you were introduced to 9.8 meters per second as the gravitational acceleration, that is actually the strength of the gravitational field near the surface of the Earth. You can write it in units of 9.8 newtons per kilogram, and that tells you that if I put 1 kilogram in Earth's gravitational field, it's going to experience a force of 9.8 newtons. If I put 2 kilograms in Earth's gravitational field, it's going to experience a force of 19.6 newtons, etc. So I can characterize the space around the Earth and characterize how strong this thing that I'm calling the gravitational field is around the Earth, and then I can use that information to figure out how large of a force I will exert on any mass that I happen to put into that gravitational field. We do very similar thinking with charge. If I have a little point charge that has an amount of charge Q, and I put it in the vicinity of a large charged object, there will be an interaction force between those two objects. If Q happens to be positive, the forces will be repulsive and these two objects will push away from one another. If Q happens to be negative, the force will be attractive and Q will be pulled towards the positively charged object. However, similar to what I did on the left, I can say, well, what if we take away this little test charge Q? Now there's no longer any electrical forces in this situation because I only have one object and I need to have at least two objects to have a force. But I can imagine the area around this charge being filled with something I'm going to call the electrical field, and that electrical field has a certain strength at certain points. And then I can imagine if I were to insert a test charge back into here, I can talk about how much force that test charge feels from the field if I have information about how strong the field is at any given point, rather than calculating the force between that charge and this larger object down here. Again, if you have 2-point charges, the concept of field doesn't really buy you anything. But when you have many, many, many charges, like you might imagine there are, well, at least I've drawn 10 different charges in this object, there would be more forces that I'd have to calculate at any point charge, and it would turn into a more complicated vector addition problem. So an electric field is a vector quantity in that direction matters, and the direction depends on the arrangement of charges that you have. In fact, electric field is defined in terms of the electric force. So I'm not sure if you've seen the 3 equal signs before, but that means defined to be, and in some sense it's a stronger equals. So what we're saying up here is that the electric field is defined to be equal to the electric force on a test charge within that field divided by the magnitude of the charge itself. Positive and negative charges experience opposite forces in identical electric fields. So if I have an electric field that is pointing in a certain direction, and we'll see some examples of this as we go on, if I put a positive test charge in that electric field and let it go, it will accelerate in one direction. If I put a negative test charge in that electric field, it will accelerate in the opposite direction. Because we can rearrange that definition up here. If electric field is equal to the force divided by the charge, that means the force is equal to the charge times the electric field. The electric field would have a fixed direction. But if this charge is positive, the force is going to be in the direction of the electric field. If the charge is negative, the force is going to be in the opposite direction to the electric field. The principle of superposition that we talked about briefly with the forces still applies. In other words, if I can figure out what the electric field contribution is from object A and what the electric field contribution is from object B, I can combine those two contributions to figure out what the overall electric field must be at a given point. And I can use Coulomb's law to find the electric field due to a point charge, and this is again only a point charge. There are other ways of figuring out what electric fields are from more complicated arrangements of charge. But if we take Coulomb's law, which we've assembled recently, the force is equal to the Coulomb constant times the product of the two interacting charges divided by the distance between those charges squared. Well, if the electric field is equal to the force divided by the magnitude of that test charge, the test charge will cancel out of this equation, and it will just leave me the Coulomb constant times the other charge in the interaction divided by the distance to the point where I'm calculating the strength of the electric field at squared. For many of us, having a drawing of what an electric field might be visualized like can be helpful when we're trying to think about what an electric field is and how it operates. And so there are two primary ways of drawing electric fields. One is through a concept of field lines. The other is through a concept of vector fields. We're going to work a little bit with the latter when we work on the electric field simulation lab. But I'm going to talk in this discussion about both ways of representing these things, because in certain contexts one is more useful than the other, and vice versa. So if you have a field line diagram, they often look like this. So this is an electric field representation around a positive point charge. This one is around a negative point charge. And then the field gets more complicated if we have, say, two positive point charges or a positive and a negative point charge. Vector fields look a little bit different when we draw those maps. And so here's what the vector field looks like around a positive point charge. Here's what the vector field looks like around a negative point charge. Here is a vector field around a positive and a negative point charge. And then this is not even a point charges, it's a more complicated vector field that would be created by a whole distribution of charges. So let's take these representations one at a time. We'll start with field lines. And there are some rules if you're going to draw electric field lines to represent the electric field. First, field lines are, by convention, somebody made up the rule, directed away from positive charges and toward negative charges. So you'll see here, given that the field is a vector quantity, we've drawn arrows, and those arrows have direction pointing away from positive charge and towards negative charge. Field lines terminate on charged objects or at infinity. Well, we're not going to draw infinity, but the field lines actually end when it gets to the charged object. Now, looking ahead to our third unit on electromagnetism, this is slightly different than when we draw magnetic field lines, and we'll come back to that discussion a bit later when we talk about magnetic fields. Field lines never cross because a field only has one direction at a given point. Again, that field might be created by multiple objects, but the overall direction of the field at any given location in the neighborhood of those objects is only a single direction, and it's the combination of the influences from all of the objects that are creating the field. The number of field lines entering or leaving an object is proportional to the charge on the object. So these diagrams don't directly show that because we don't show the size of these charges. But if this was my field line diagram for this positive charge, if for some reason I took this positive charge away and I replaced it with one that had twice as much charge but was still positive, I should draw my field line map having twice as many electric field lines as the one that I've shown right here. Finally, the field line density indicates the strength of the electric field. So where are the field lines the closest together? Well, the field lines are closest together here, closest to the charges, and that's where the electric field is the strongest. And as you move away from point charges, the field line density drops, and that tells you that the strength of the electric field drops as well. So, given those rules, pardon me, here's a question to think about. There is an electric field line diagram, but there are at least 3 errors in the electric field diagram above. Can you see what they are? And I would encourage you to pause the lecture at this point and see if you can figure out what all 3 errors are. The 3 errors come in, let's see, violating Rule 3, field lines never cross, here at point P. You'll see that they've drawn one field line going in this direction, one field line going in that direction, and you can never have 2 field lines that cross, because that would be saying that the electric field at a given point is actually in 2 directions. It would be like saying if you stand in this certain spot on Earth, the gravitational field pulls you both down and to the left, and then that can't be the case. They've also violated Rule 4, the number of field lines entering or leaving an object is proportional to the charge of the object, because, let's see, this charge that has 4Q has 1, 2, 3, 4, 5, 6, 7, 8 field lines exiting it, and that means there are 2 field lines drawn for every 1 Q of charge. Well, that means up here when I have 2 Q of charge, I should have 4 field lines coming in. Down here where I have minus 1 Q of charge, I should have just 2 field lines coming in. And again, here with minus Q, I should have only 2 field lines as well. And they also violate Rule 5, that field line density indicates field strength. And the place that that's violated is over here in between the 4Q and the minus Q charge. These field lines are all drawn parallel to one another, which would suggest that the field is just as strong right here as it is right here, as it is right here. In fact, the whole region between those 2 point charges, where in fact the field would decrease as you moved away from one charge until somewhere in the middle of those 2, and then increase again in strength as you moved closer and closer to the other charge. I would encourage you, if you have some scrap paper that you're working with, to try to sketch a correct electric field diagram for this charge arrangement. I didn't do so on this slide, but essentially you could leave 8 field lines coming out of this 4Q charge, but 4 of them would have to then be directed to the minus 2Q charge, and they would look much like here where they diverge away from one another and then they come back in on one another. But 4 of them would go between here and here. 2 of them would go between the 4q and the minus q, and 2 would go between this 4q and the minus q. And in both those cases, they would again diverge away from one another and then come back towards the charge when it got closer to the minus q point charge. The other representation of fields is the concept of a vector field, and a vector field diagram looks like what we've shown on the right there. Vector field vectors rather are directed by convention again away from positive charges and toward negative charges. So the direction idea in these field diagrams hasn't changed at all. But what we do instead of drawing continuous lines is you take equal intervals on a field map, essentially a grid. If you look at the center of each of these arrows, it forms a grid pattern on here. And then the field vectors themselves indicate how strong the field is at that point in space. So right here, how strong is the field and what direction does it point? Well, I point my arrow in the direction of the field, and I use some way of indicating how strong the field is there. But you can see from these diagrams there's a couple of different choices. The diagrams on the top do it by how bright or bold the field vector arrows are, and so you'll notice they dim as they move away, and that's to indicate a weakening electric field. Or you can draw it by arrow length. So if you look at the field vector diagram here at the bottom, near the point charges the arrows are drawn quite long, and then when we're out here quite a ways away from those point charges, the arrows are drawn very short, so the vector length there is indicating how strong the field is at a given point. And so sometimes color is used in a visual representation, sometimes vector length. Obviously, if you are hand drawing a vector field diagram, you are more likely to do the length of the arrow because it can be difficult to draw different color strength or different colors of arrows in a diagram like that, but either can actually be used. So, a question to think about in terms of field vector diagrams. A positive charge plus q experiences the 3 forces shown when placed at 1, 2, and 3. So if I put it at this location 1, it feels a force in this direction, and the force is stronger here than it is if I place it at 2, where the force is now directly to the right. Place it over at 3, the force is weaker and it's down and to the left. So again, if you have some scratch paper, see if you can pause the presentation and sketch electric field vectors at each of those 3 points. If you've done the sketch, it should in fact look exactly the same as this sketch. Now, the arrows don't have to be the same length as these arrows, but they should be proportional to those arrows. And so the field would be strongest at point 1, then at point 2, then weakest at point 3. And in fact, you can keep this exact same diagram and just change all of the F's to E's representing the electric field. In fact, here is that diagram. I did just that. The electric field now is shown at points 1, 2, and 3 on the diagram below. Can we determine the field right here at this location in space? The answer is no. All a vector field diagram does is tell you the strength of the field at the point that's either at the end of the arrow in this particular representation, or sometimes it's in the center of the arrow, but it's those equally spaced grid points where you know, okay, I know the strength of the field right here, I know the strength and direction of the field right here, I know the strength and direction of the field right here, but at other points in space, I don't know what the field is doing exactly at this point up here. It just happens to be in the middle of the vector arrow that we've drawn. What would the force vectors look like now if we put a negative q charge at point 1? Well, again, electric field is defined to be the force divided by the charge, or we can say the force is equal to the charge times the electric field. Well, if we put a negative charge at point 1, the charge is going to experience a force in the opposite direction to the electric field. So the force vector at point 1 is now going to point down and to the left on a charge of minus q, over straight to the left at point 2, and up and to the right at point 3. If instead we put a positive charge, but that positive charge had a magnitude of 2q rather than 1q, then the force at each of these points, including point 3, would be in the same direction as the electric field, but the force vector itself would be twice as big as it was for the 1q charge, because the force is proportional to how big the charge is, just like the gravitational force on a mass ends up being proportional to how much mass you have. So another question about these vector diagrams. Here are two electric field vector diagrams. Which of these, if either, are possible? And I would again encourage you to pause, think about it, and come to an answer before you listen to the rest of this. And the answer is that both of these situations are possible. Again, many people say, oh, B is not possible because field lines cannot cross, and that's absolutely true. But these are field vector diagrams, and again, the arrow is just telling me how strong the electric field is at this point, and how strong the electric field is at this point. And if I'm using vector length to indicate the strength of the electric field, it's very possible that those vectors themselves might cross, even though the electric field can't have two directions at either of these points that are represented by the dots on the diagram. We're going to wrap this up by solving a couple of problems with the concept of electric field. So imagine that you have an object that has a certain amount of charge. In this case, it's minus 3.6 microcoulombs. Micro is 10 to the minus 6. And a mass of 12 grams, or 0.012 kilograms. It experiences an upward electric force due to a uniform electric field equal in magnitude to its weight. So if it experiences an electric force up and a gravitational force down, and those are equal to one another, this object is going to be levitating there, or if it were already moving, it would move with constant velocity. So we want to find the direction and the magnitude of the electric field, and then think about what would happen if we doubled the electric charge on the object while the mass remained the same. What would that mean for the acceleration of the object? Well, you don't have to do it, but I find it very useful in almost all physics problems to draw a little sketch of the object that I'm analyzing and label the things that I know about it. So here's my object. There's a force on the object from the electric field in the upward direction. And there's a force on the object from the earth in the downward direction, which is that's the notation I'm using to label my forces. So I'm going to apply Newton's second law, and you'll find that we need Newton's laws and a few of the other general physics ideas, general physics 1 ideas rather, quite frequently when we do this analysis. Newton's second law says the net force on an object is equal to its mass times its acceleration. That means the force on the object due to the electric field minus the force on the object due to the earth, which is the net force part of the equation, has to equal to 0 because these are balanced forces, and when the net force is equal to 0, there's going to be no acceleration. That means, of course, that the two forces are equal in magnitude to each other, and I know that the force on the object due to the earth is equal to its weight, so its mass times the strength of the gravitational field, or as you've probably called it, the acceleration due to gravity. So that's 0.012 kilograms times g, and I told you I have an affinity for making g 10. You can make this 9.8 here, but I just do 10 because it's easier for me to do the math in my head with 10. So that's about 0.12 newtons, or 0.11 whatever if you use 9.8. So the electric field is defined to be and equal to the strength of the electric force divided by the amount of charge. The object itself, we've figured out, has 0.12 newtons of electric force on it. The charge is 3.6 microcoulombs, or 3.6 times 10 to the minus 6 coulombs. And if you calculate that out, the strength of the electric field is 3.3 times 10 to the 4th newtons per coulomb. Notice that I'm using just the magnitude of the charge here. I'm ignoring the fact that I was told that the charge is negative, because I'm just working out the magnitude of the electric field, the size of the number, and I'm going to think momentarily about what the direction of that electric field is. In fact, let's do that now. Negative objects, which this one is, feel forces that are opposite in direction to the electric field that is being applied to them. And so because the force from the electric field on this negative object is up, that must mean that the electric field itself is in the downward direction. And so the overall electric field, if we write it with magnitude and direction, would be 3.3 times 10 to the 4th newtons per coulomb down, or if you'd assigned a coordinate system, you might say 3.3 times 10 to the 4th newtons per coulomb in the negative y direction, or something similar. Alright, B, if the electric charge on the object is doubled while its mass remains the same, find the direction and magnitude of its acceleration. There is a force upward now on the object that is twice as big as it was. The force on the object from the Earth remains the same since we haven't done anything to significantly change the mass of the object. It's true that if you're going to double the charge, you have to change the number of electrons, but it turns out the mass of the electrons is so minuscule that it has a negligible effect on the mass of the object. So now we have a situation where there is a net force. The net force is the difference between those two forces, or 0.12 newtons up. And if we then apply Newton's second law to say the acceleration is equal to the net force divided by the mass, the net force up is 0.12 newtons, the mass is 0.012 newtons. Again, that's math I can do in my head, and that acceleration is 10 meters per second squared. By the way, if you worked with g being 9.8 meters per second squared, you're going to get 9.8 when you get here. The acceleration now is in fact equal to the size of the acceleration that gravity would put on this object, but it's in the upward direction because the force, the net force is in the upward direction, so this object would accelerate up. One more, just to think a little bit about vectors and direction. In this particular drawing, it shows two situations in which charges are placed on the x and y axes. They're all located at the same distance from the origin. So first of all, we don't want to do any formal calculations. Does the electric field at the origin in part A have a magnitude that's greater than, less than, or equal to the magnitude of the field at the origin in part B to justify your answer? Notice, first off, that we're talking about the origin where there is no actual charge, and this is one of the things that people struggle with thinking about electric fields. But again, electric fields is our way of describing the properties of a location in space, and that location doesn't need to be occupied for there to exist an electric field at that location. But if it helps, you can think about, well, what would happen if I put a little test charge right here at the origin? Which way would it move? Well, it turns out that in both of these situations, the electric field in the middle is going to be the same. So, like I said, what I do is I imagine, okay, if I put a tiny little positive test charge right here at the origin, what's going to happen to it? Well, let's see. In situation A, there's going to be a force from this 2 microcoulomb charge, and it's going to push the object to the right, and it's going to be a force proportional to 2 microcoulombs. There's going to be a force also to the right from this minus 3 microcoulomb charge, because the positive and negative will attract, so that force will be proportional to minus 3 microcoulombs. So overall, I'll have a force to the right that's proportional to 5 microcoulombs. I'll also have a force in the upward direction that is proportional to 5 microcoulombs from the charge that's at the top of the y-axis here. In situation B, I'll have a force to the right proportional to 4 microcoulombs from this charge, and I'll have another force to the right proportional to 1 microcoulomb from this charge. So overall, that's 5 microcoulombs to the right. I'll have a force in the downward direction from this 1 microcoulomb charge, and I'll have a force proportional to 6 microcoulombs in the upward direction from this charge. So overall, the vertical force is going to be proportional to 5 microcoulombs and in the upward direction. And so those two situations actually have forces that are going to be equal. And because the net force would be the same on a positive test charge that we stick there in the middle of the charge arrangement, that means the electric field at the origin in both those cases would be equal. By the way, because it's equal at the origin doesn't necessarily mean it's equal everywhere in this scenario, and it would be unsurprising if we talked about the electric field at a different location, say up here, to find that it was very different in these two charge arrangements. Alright, so what is the electric field at the origin in each of these cases? Well, a convenient thing about doing part A first and thinking about the scenario is we don't have to blindly rush through a bunch of extra calculations. We already know what to expect in terms of the answer. It's the same in both situations, so we really only need to solve it for one. The electric field due to a point charge is again equal to K times the strength of that point charge divided by the distance to the location where you're calculating the electric field squared, because electric field is defined to be the force divided by the test charge magnitude. So I'm just going to choose situation A because it only has 3 calculations to do rather than situation B, which would require 4. So the electric field from the 2 microcoulomb charge would be the 8.99 times 10 to the 9th Newton meters squared over coulomb squared, times the amount of charge, so that's 2 times 10 to the minus 6 coulombs, divided by, let's see, it's 6.1 centimeters, so that's 0.061 meters, all squared. And I just cancel out units here. Meters squared is going to cancel with meters squared down here. One of these coulombs is going to cancel one of the coulombs in the denominator, and my answer is going to be left with units of newtons over coulombs. And the magnitude of the answer is 4.8 times 10 to the 6th newtons per coulomb. You can do a similar calculation for the minus 5 microcoulomb charge. Again, I'm just doing the size of it, and I'll worry about the direction momentarily. It comes out to be 1.2 times 10 to the 7th newtons per coulomb. The one to the right, due to the minus 3 microcoulomb, is 7.2 times 10 to the 6th newtons per coulomb. So if I draw a vector diagram with all of those, here's my upward force, 1.2 times 10 to the 7 newtons per coulomb. And here are my 2 rightward forces, 4.8 times 10 to the 6 and 7.2 times 10 to the 6. Combined, they are 1.2 times 10 to the 7th newtons per coulomb to the right. I actually have a situation where I have a vertical and horizontal component that are equal to each other. And so the overall electric field is the vector sum of those two. And you can use the Pythagorean theorem to deduce that it's about 1.7 times 10 to the 7th newtons per coulomb. And it's oriented at 45 degrees above the x-axis because the vertical and horizontal components are equal to one another. Again, we've already thought about it, and we know just from inspection that case B is the same magnitude. So this concludes the online lecture on electric fields and field lines. Hopefully this is a useful resource to those of you that are watching it. And as always, if you notice any errors in the presentation, please let me know.